Okay, so to do an example of mixtures, I'm going to do one where we need a certain amount of a final product. Actually, I'm going to do two examples. I'm going to start out with one where we have a set amount of one of the ingredients, and that's a little bit simpler. So let's look at this. Let's ask how much, for dealing with solutions, 42% solution should be mixed into 120 milligrams of, let's see here. Let's go 27% solution to create 32% solution. So one thing I always look at in these are, what are my two ingredients? And this is, chemical solutions, medical solutions, whatever you want to look at. But it could be investments, two component investments in the final product. So we have our ingredients, our components, and then our final product. And in this case, we're starting out with what 2%? 42% and 27%. Very good. So we're combining 42% with 27%. And we want our result to be 32%. The amounts for those. The only amount we have is 120 milligrams, and that goes with 27%. We're asked how much 42%. So I'm going to let the amount of the 42% be X. The amount of the final product then is, if we have X milligrams and 120 milligrams, that has to add up to give us X plus 120. So the amount of the final product is just the two ingredient amounts added together. So the amount of active ingredient, or the amount of chemical medicine, if it's a medical application, in a solution, is the concentration, or the percent as a decimal, times the amount. So 42% as a rate is 0.42 times the amount of X. We add that to the other ingredient, the 27%, as a rate is 0.27 times its amount is 120. And the amount of the ingredients has to equal the amount of the final product. That's 32%, so that's 0.32 as a rate, times its amount of X plus 120. And now we go back to solving an equation. Remember our steps for solving an equation. The first step is combine what you can on either side. Well, on the left side here, nothing to do with the 0.42x, but we can multiply 0.27 times 120. Oops, that didn't work. 0.27 times 120 is 32.4. That's all we can combine on the left side. On the right side, we can multiply the 0.32, distributing it through the parentheses. 0.32 times x is 0.32x. 0.32 times 120, thank you, 38.4. So we've combined what we can on either side. Remember, the second step in solving equations was then to look to see if the variable appears only once or if it's on both sides. Here it's on both sides, which means we have to get rid of one of them. We'll usually get rid of the smaller one, in this case, the 0.32. It's positive, so we get rid of it by subtracting it. We have to subtract 0.32x from both sides. So 0.42x minus 0.32x is 0.1x plus 32.4 equals 38.4. So now we've combined everything we can combine. The variable appears only once, so now we can go ahead and start to solve. What's our first step to do that? Subtract 32.4. So you get 0.1x equals 6, and then divide by 0.1. So x equals 60. So now there's a couple things we have to do. We have to go back, make sure we know what that variable represents, and then make sure we've answered the question. So x represents the amount of 42% solution, that's 60. The units are milligrams. And yes, we're asked how much 42% solution. So 60 milligrams of the 42% solution is the result we want. It's a little more difficult when we're, instead of given the amount of one of the ingredients, we're given the total amount that we want. And that's usually the way things are done. Let's go switch over to an investment problem. Let's say Sam invests $8,000 in a mixture of 3% and 6% investments. Actually, let's do 3% and 7%. Make things a little easier on this. I intentionally use the word mixture here because it is just like the other mixture problems. It's the same concept. If Sam averages 6% gain, find the amount invested in each. So here again, we have our ingredients, or the two components in this case, 3% and 7%. The things we are mixing together, and we want our result to be what? 6% overall. The only amount we know here is the 8,000, which is the total amount. But just like up above, the amount of one ingredient plus the amount of the other ingredient has to equal the total. Up above, we had x plus 120, so we got x plus 120. Well, here we have to work backwards. Let's let one of these values be x. I'm going to let the amount of the 7% investment be x dollars. So the number of dollars in the 3% investment would be 8,000 minus x, the total minus x. So now then the formula works out to be 3% as a rate is 0.03 times 8,000 minus x combined with 7%, 0.07 times x has to equal our final amount, 6% of 0.06 times 8,000. So now again, it's a matter of going through our process of solving equation. First step is to combine what we can on each side. So on the left side, I'm going to distribute 0.03 times 8,000 is 240. 0.03 times negative x is negative 0.03x. And we have the plus 0.07x. I can still combine on the left side. I've got negative 0.03 and positive 0.07x. So that comes out to be a positive 0.04x. The 240 didn't change, that just stays there. We've combined everything we can on the left side, we go to the right side. 0.06 times 8,000 is 480. So we've combined everything we can on the right side. So now that we've combined everything, we check to make sure that the variable is only on one side. And here it is, our x is just on the left side. So what's our next step to solve this? Subtract 240, good. So 0.04x equals 240, and then divide by 0.04. X equals 6,000, perfect. So again, we go back to make sure we know what x represents. X, $6,000 is the amount in the 7% investment. We were asked to find both amounts. So in the 3% investment, it's 8,000 minus 6,000, or 2,000. So there's $2,000 in the 3%. Any questions on those? So those can be a little tricky. Make sure your homework 2 A, B, and C. They had other due dates, but the absolute due date is today. And quiz 2 is due tonight at 11:59 p.m. Did anybody have any questions on any other material that could be on quiz 2, or anybody do their first attempt and have questions that they are not sure about on quiz 2? Okay. So let's hit our new material now. That catches us up from last week's. Today we're going to talk about displaying numbers. We talked a little bit about displaying numbers when we dealt with integers and stuff. There's a couple of ways to display numbers on a number line. One way we talked about displaying numbers is a mechanical definition of numbers so that we can actually use them to do calculations. To display x equals 7, we could use a vector, which is just a fancy word for an arrow that starts at 0 and goes to 7. That's the vector for x equals 7. But today we're going to be looking at displaying multiple values at once. And for displaying multiple values at once, that vector is clumsy. Great for calculating, but not good for just representing values. So the easier way to represent just the value x equals 7 is a dot at 7. Well, it's kind of boring if we just place dots on there. We might do an equation like 3x plus 1 equals 10. How would we solve that? We subtract 1, good, to get 3x equals 9. And yes, we divide by 3 to get x equals 3. And we could represent that up here, put a dot at 3, and we've represented the solution to that equation. But what we're looking at today is not equations, but something called inequalities. Inequalities are things that are not equal. And there's a few different symbols we can use to express them. X is less than 6. Just to talk about some values here. If x equals -2, is that true? Is -2 less than 6? Yes, it is. If x equals 0, is that true? Yes, 0 is less than 6. If x equals 3, is that true? Yeah, 3 is less than 6. If x equals 10, no, 10 is not less than 6. If x equals 6, is that true? No, it's not. 6 is not less than 6. There's a symbol very closely related to that one. It looks like that. That means x is less than or equal to 6. In that case, if x equals 6, is that true? Yes, it is. That's the only difference between that two expressions, is this expression down here, x can be 6. Up here, it cannot be 6. And of course, we go the other direction. We might have x, y, whatever variable we're using, is greater than 2. So there, if y is equal to 3, is that true? How about y is equal to negative 1? Negative 1 is not greater than 2, right? So no. Well, y equals 0. No. Y equals 2? No. Again, we could have y is greater than or equal to 2. Then y could equal 2. Well, when we see this, there are several different ways we can display the solution. One is something we call solution set notation. Solution set notation is a little bit of a cop-out because in some cases, like this simple inequality, y is greater than 2, all we're really doing is repeating the equation, the inequality. Solution set notation uses these squiggly brackets like that. And since our variable is y, we say all values of y such that y is greater than 2. Well, again, that's kind of a cop-out because again, here all we did was repeated the inequality, y is greater than 2. This notation here is saying all values of y such that it meets this condition that comes after that vertical line there. But where it's really more useful is if we have a more complex inequality. We might have 3y minus 5 is less than or equal to 7. Now, looking at this, that inequality looks different than an equation, but we can treat this very, very similar to the equation 3y minus 5 equals 7. With some notable exceptions that we'll point out as we run into them, they work the same. So what would be the first step we would do to solve that equation? We would add 5. So over here in our inequality, we can do the same thing, adding 5. Just like you have to add 5 to both sides of the equation, we add 5 to both sides of the inequality. So it cancels out the minus 5, giving us 3y on the left side. The symbol does not change. It stays less than or equal to. On the right side, 7 plus 5 is 12. What would our last step be to solve that? There we go. Divide by 3. Perfect. So that cancels out that 3, leaving us with just y. Y is less than or equal to 12 divided by 3 is 4. So y is less than or equal to 4. So our solution, the way we'd list our solution is the solutions to that equation, 3y minus 5 is less than or equal to 7, is all values of y such that y is less than or equal to 4. Make sense? Back to our visual representation of this. Referred to as a graphical representation. We can do it on the number line. So y is less than or equal to 4. We plot the boundary point. Our boundary point is where it separates the solutions from the non-solutions. And that's just at the value that's on the other side of the inequality from our variable. Here, that's 4. This is where 4 is on our number line. That's our boundary point. So either one side of that boundary are the solutions and the other side are not. This is less than or equal to, which means the less than side goes this way. That is where the solutions are. What if we're not sure? We can take a test point. 0 is pretty obviously on this side, on what we've colored in as the solution side of that boundary. If I put 0 in for y, if y equals 0, is that inequality true? Yes. So yeah, we shaded in the right side of that number line. Now, one thing that's very important is what I did right here. Above the 4, I made a solid dot. That solid dot is including the 4. The alternative would have looked like this. Over the 4 and shading in. That would have been referred to as an open dot or an open point. What does that mean about the 4? There you go. 4 is not included. So that means is we can be any number right up to the 4, but we can't be 4. So yes, and the representation that would be there, that would be y is strictly less than 4 rather than less than or equal to. This is y is less than or equal to 4 up here. That's why we have the closed dot includes that that boundary point is included in the solutions. So we might have 5x minus 1 is greater than negative 16. What should we do to try to solve this? Add 1. We're going to try to get that variable, in this case x, by itself again. So we're going to add 1. So that 5x is greater than negative 15. What would be next? Divide by 5. Perfect. So we have x is greater than negative 3. That's our solution. For putting that in solution set notation, all values of x such that x is greater than -3. If I'm putting it on a number line, where does my dot go? -3. Open dot or closed dot? Open dot. Hollow dot, if you will. Points to the left or to the right? The right. This here corresponds to that arrow on the number line. It goes towards that arrow. Now again, to double check, 0 is in that shaded region in my solution set. Let's make sure that works. Is 0 greater than -3? It sure is, so that is true. So those are the two ways that we could express solutions to that. Now, of course, coming up in a few weeks, we're going to learn a third way using interval notation, but we're not to that quite yet. So there will be a third way of representing these. In your notes, I want you guys to try a couple here. So 2x plus 7 is greater than or equal to 15. And 4x minus 1 is less than 11. Try those in your notes. I want the answers both in solution set notation and plotted on a number line. We'll talk about these in about a minute. So we have the solution set notation, and then for our number line, our boundaries at 4, open dot or closed dot? Closed dot, point to the left or to the right? The right. It is greater than. So for the second one down here, what's our first step in solving that? Add 1. Good. 4x is less than 12 now. What's our next step? Divide by 4. X is less than 3. So solution set notation, all values of x such that x is less than 3. On the graph, the dot goes at 3, open dot or closed dot? Open dot, pointing to the left or the right? Left. I'm cheating and putting them both on the same number line, but you get the picture, right? So, exactly. Yeah, this points to the left, the arrow goes to the left. Or it represents the arrowhead on the left end, we point towards that arrowhead. And we can always test. Like for the second equation here, the green one, if I put 0 in for x, does 0 make this true? Let's put it back in the original one just to check it. 4 times 0 minus 1, is that less than 11? Yeah, 4 times 0 minus 1 is -1. That's yet less than 11. That works. So the 0, the portion that includes 0 is colored in. That's the correct answer. That's what we want. Up here, if we tried 0, we'd have 2 times 0 plus 7. Is that greater than or equal to 15? Here, I'm going to write it over here so we got more room. Well, 2 times 0 plus 7 is 7, right? Is that greater than or equal to 15? No. So 0 is not in the solution set of that. So you can see the brown points away from the 0, so that it doesn't include the 0 in the solution. So let's look at another one here. Let's do 11 minus 2x is less than or equal to 3. So to start solving this, the first thing I would have to do is subtract 11. Good. So I now have negative 2x is less than or equal to negative 8. What's my next step? I have to get rid of the negative 2. Since it multiplies x, I divide by a negative 2. So that gives me x is less than or equal to a positive 4. Now notice I put that less than or equal to in there kind of lightly because there's something significant that happens here. If I tried to graph this, move this over just a touch. Of course, here's the 4. Less than or equal to would be a solid dot pointing to the left. Less than would be to the left. But if I try 0 here, 0 is obviously in the solution set of my graph, so it should make this true. If it were outside the solution set, it should make it false. I put 0 in here, 11 minus 2 times 0, less than or equal to 3. Well, what is 11 minus 2 times 0? 11. Is that less than or equal to 3? No. So something went wrong here. The thing that went wrong is right here. We divided by a negative 2. We divided by a negative number, period. When we divide by negatives or multiply by negatives, weird things happen in our inequalities. If you really get right down to it, you're not allowed to multiply or divide by a negative. When we have 11 minus 2x is less than or equal to negative 8. To solve this, technically what we should do is we've got to make the coefficient on our variable positive. To make it positive, and we're not allowed to multiply or divide by a negative, the only way to do that would be to add 2x, to basically eliminate it and wipe it out. But what do we have to do if we add 2x on the left side? Add 2x on the right side. So that's going to give us 11 is less than or equal to negative 8 plus 2x. Now, the variable and its coefficient are positive. To solve this, what would we do first? Add 8. Did I copy that down the same? That should be a 3, not an 8, shouldn't it? Wow. Let me change that. This was a 3, not an 8. This should be a 3. So it should be 11 is less than or equal to 3 plus 2x. I'll pause for a second and let you fix my mistake in your notes. So we started out with 11 minus 2x is less than or equal to 3. We added the 2x to both sides to get rid of the negative 2x. We have 11 is less than or equal to 3 plus 2x now. No, it was a positive 3 to start out with. Sorry for the confusion on that. So now we're solving for the 2x. Now we start out by subtracting the 3. So we get 8 is less than or equal to, this 3's gone, 2x. What's next? Divide by 2. 4 is less than or equal to x. Now, we've got our solution we didn't have to multiply or divide by a negative. There's a little bit of an issue with this. When the variable comes after the inequality symbol, it really doesn't make sense. I mean, we're not looking at a number line and somewhere there's an x and we're less than or equal to that. That's not what we want to graph. X has to be the variable, should become first. So we need to be able to switch the order of an inequality. So 4 is less than or equal to x. Is equivalent to an inequality where the variable is first. X comes first, 4 would come after it. The symbol has to stay consistent. That doesn't mean we use the same symbol. By consistent, I means it compares the numbers in the same way. This symbol here is indicating which one is larger, 4 or x. X is larger. So I have to put a symbol in here that indicates the x is larger. X is greater than 4. X is bigger than or equal to 4. What you'll notice is this symbol points towards the 4. This symbol continues to point towards the 4. This symbol includes the or equal to. This sun also includes the or equal to. So our symbol stayed consistent. We're going to talk about this a little bit more in just a minute. But let's go back up to this problem here. So what we get is x is greater than or equal to 4. So the boundary is still 4, but we're finding it's greater than or equal to, not less than or equal to. And we said the trouble all started right there with that negative. Well, what we did here by adding the 2x and solving it that way is technically the way you should do an inequality. But all of us have been taught a shortcut for avoiding, because let's face it, this got messy down here. That's a lot of work. What we were taught for avoiding it starting just like we started out the first time, we subtract the 11. Negative 2x is less than or equal to negative 8. And then we'll go ahead and divide by the negative 2. But I just said several times in the last few minutes, we can't divide by a negative. Well, we can't divide by a negative unless we adjust for it. Down here at the end, we ended up having to switch that symbol, that inequality symbol. When we multiply or divide by a negative, as long as we do that equivalent switch of the symbol, we're okay. So we divide by the negative 2 to cancel out that. We've got x. Negative 8 divided by negative 2 is 4. But since we divided by a negative number, the inequality symbol has to switch. We flip it over. So notice the same symbol we had down here. So x is greater than or equal to 4. So that's a big thing to make sure you keep straight. When you multiply or divide by a negative in an inequality, that symbol has to flip. So let's look at something like this. 7 is less than negative 3x plus 13. Where do we start? Subtract 13. 7 minus 13 is a negative 6. So that 13 is gone on the right side. So negative 6 is less than negative 3x. Now what? Correct. Perfect. Very good. We divide by -3, eliminates that -3, we have just x. -6 divided by -3 is +2, and you got the second part of it too. Since we divided by a negative, that sign has to flip. So 2 is greater than x. Now we can't graph it like that. We need the variable first. So this is going to become x. What's the symbol going to be? Is less than 2. Notice it still points at the x. So where's our boundary going to be? At 2? Open or close dot? Open dot. Point to the left or the right? To the left. Or in solution set notation, all values of x such that x is less than 2. I want you guys to try one in your notes. $11 is greater than or equal to 23 minus 4x. I'll give you a couple minutes to work on it. Let's see how you're doing so far. So to solve this, what's our first step? Perfect. We'll subtract 23. What's that going to give us? -12. Greater than or equal to -4x. Good. That 23 is gone. What's our next step? We divide by -4. Perfect. What's that give us? Careful. 3 is less than or equal to x. Because we divided by a negative, got to flip the symbol. So for solution set notation, what would we write? All values of x such that perfect. X is greater than or equal to 3. We got to flip this around. It's pointing at the 3, so it has to continue to point at the 3. To plot it on the number line, what's our boundary point? 3. Open or closed? Closed because it's or equal to. Left or right? Right. Greater than or equal to. Any questions there? Okay, we can have all sorts of other complications that come into these, just like with any of our equations. We might have 7x minus 2 is less than 3x plus 12. Now, just like any of our equations, we follow the same steps. The third step is to solve. Before that, there's 2 steps to go through. Here we have to do that first step, combining on either side. Is there anything to combine on each side of this? No. The second step is make sure the variable is on only one side. Is the variable on only one side here? No, so we have to get rid of one of them. Which one do we get rid of? The 3x, and we subtract it. Of course, we have to subtract it from both sides. We'll subtract it from the 7x on the left side. What do we get? Four x minus 2 is less than 12. Now the variable appears only once, so now we are able to start to solve this. What do we do next? Add 2. So 4x is less than 14. And then we divide by 4. We get x is less than 3.5 or 3.5, however you want to list it. So solution set, all values of x, such that x is less than 3.5. Number line, of course, boundary is at 3.5. Open or closed? Open. Left or right? Left. Perfect. I want you guys to try one of your notes. It's going to be a little bit different than that. I'm going to take actually a couple of steps up in difficulty just to see how you guys handle it. Give that one a shot in your notes. Again, give your answer in solution set notation and on a number line. I'll give you a couple minutes. Is at -2. Open or closed? Close, left or right? Left. Perfect. Any questions on those? Okay. We're not going to get much more complicated than that for now. Later on in the course, we'll come back to more possibilities with those. There's a lot of things you can do with inequalities. We can deal with two variable inequalities. We can deal with rational inequalities, even in just a single variable. Those are things that will come later on. For now, kind of a little stepping stone before we go on to our next topic, data graphs. It's kind of an aside, but as we're talking about graphing, we do have to talk about data graphs. And there are several types of data graphs that we run into. But first we have to talk about types of data. We can have numerical data, and we can have categorical data. Most of us are used to graphing categorical data, even though it has numbers in it. The things that are being graphed are categories and their frequencies. An example might be favorite color. If I ask people what their favorite color is, their answer to that question is not going to be a number, not numerical. It's going to be a word or a category. Your answer puts you into the category of people that like red or green or blue or whatever. So let's say we give people 3 choices. Red, blue, green. The frequency with which they respond. Let's say that out of 20 people, 8 people said red, 5 people said blue, and 7 green. Probably the simplest data graph we can create from that is a bar graph. We're all familiar with bar graphs. They can be done one of two ways. Vertical. In a vertical bar graph, our categories go across the bottom. Some sort of label here. We call that color or even favorite color. And of course, frequency or number chosen. And we have to make sure we number up to the highest frequency. Here that would be 8. So we actually number up to 10, so we're at least that frequency. And we go ahead and put our bars on there. Red goes up to 8. Blue goes up to 5. Green goes up to 7. Couple of things. Notice I'm very careful to make the bars really close to the same width. That wasn't perfect. Making the bars wider or narrower from one to the next can deceive the viewer. If I made for example, if I switch the red here to look like that, just human psychology, even though it's only slightly taller than the green, you see that just the size of it, the area of it, your brain tends to think it's much bigger. So keeping them the same, approximately the same width is important. The other type of graph that's pretty common off of this type of data is a circle or pie chart. For a circle graph or a pie chart, we usually don't graph frequency, we graph percent. To find the percent, we have to find a total. If we add these all up, they add up to 20. So 8 is what percent of 20? 8 out of 20 is 40%. 5 out of 20 is 25%. 7 out of 20 is 35%. Of course, what should those 3% add up to? It better up to 100% of the whole thing. Now, years ago, when we're talking about a pie chart or circle graph, we would have taken 360 degrees in a circle, found 40% of 360 degrees, which is 144 degrees. We would have measured out 144 degrees. We're not going to do that here. If we wanted to be that perfect, there's a lot of computer programs out there that make perfect circle graphs for us. Here, we know half a circle is about what percent? 50%, right? A quarter circle is 25. So as we look up here, we have one that's exactly 25%. That's the blue. So I'm actually going to put that in there as blue is 25%. Red is at 40%. That's fairly close to 50. I'm going to cut it across like this. That's the red. And of course, what's left here has to be the green. Not perfect, but close enough. Like I said, if we wanted it perfect, a lot of computer programs out there that will make it perfect. Numerical data works pretty much the same way. There's a couple of types. Now, this isn't a statistics class, so I'm not going to get too deep into the details of numerical data. But you can have high frequency, limited response numerical data, where you might be asked, how many classes are you taking? So it might be 1, 2, 3, 4, or 5. And not many people take more than 5 or 6 classes. So you can get the frequency for those. But you might ask somebody's age. Age, we could have students anywhere from, I think my youngest student has been 16. or through youth options, all the way up through, the oldest student I've ever had in class was 72 years old. So if we do age, we can't list out every age from 16 to 72. We have to put it in ranges. So we might do 16 to 25, 26 to 35, 36 to 45, and so on. When we go to make the graphs, we still have bar graphs, circle graphs, and so on. Bar graphs would be called a histogram if it's numerical data, but we're not going to worry too much about that. It's just a matter of having to group the data when it's numerical in certain situations. Last type of graph we want to talk about is a line graph. The graphs we've shown so far show us several different responses and compares the frequency of those responses to each other. A line graph compares one response to how that same response changes over time. We might look at satisfaction rates. The satisfaction for a company. And we might have 1990, 1995, 2000, 2005, 2010, and 2015. Now, it doesn't have to be years. It could be months, days, weeks, whatever. So look at our satisfaction rating in percent. Let's say in 1990, a particular company has a 91% satisfaction rating from its customers. 1995, it has risen to 92%. 2000, it dropped to 79%. 2005, up to 83%. 2010, 82%. And 2015, back up to 89%. Now, there are different arguments out there about how this should be done. One argument is you should always start labeling at 0 and evenly space it all the way up to whatever your highest value has to be. Well, here that's close to 100. If I label that, I'll just put the first few values on here. 1990 is at 91%. Well, that's somewhere in here. 95 is at 92%. That's somewhere in there. 2000's at 79%. Well, looking at those, you can definitely tell that 2000 is lower than the other two. We would connect them with a line. But you really can't tell if there's a difference between 1990 and 1995. It's just too crowded. Now, there are reasons why you should number from 0 up to 100. If this were a statistics course, we'd talk about those. But we don't have time here. To make this more visible, we're going to focus on the range of data. Instead of starting at 0, I'm going to start at 75. And go up to 95%. So now in 1990, we had a 91% satisfaction rating. That'd be right in here. 1995, 92%. Drop that a little bit. 91, 92%. So we can tell it did definitely go up slightly. 2000, dropped to 79%. So we can see that drastic fall. 05, it goes up to 83%. 2010, dropped a notch to 82. And 2015, up to 89. You guys get the picture. The power of graphs is you can always tell very quickly where was it the highest. Well, that's where it was at its highest value, or the lowest, right here. Even up here with our colors. The most popular color you can see is red, least popular, quickly see is blue. The weakness of a graph is finding exact values. Even in this graph over here, if I wanted to know what this value is, I'm not totally sure if that's 82 or 83 or whatever, but I can get close. So graphs are for comparisons of exact values. You still need the tables to go back to get those exact values. Okay, we are down to our last 40 seconds here. So remember, quiz 2 is due tonight by 11:59 p.m. If you don't have any of the components of homework 2, A, B, or C, make sure you have those done tonight as well. Then, of course, homework 3A is assigned today. I recommend you have it done by tomorrow, but again, that'll be due next Monday for final date. Any questions? Okay, it is that time, so you guys have a great day. We'll see you all tomorrow.